peacefully this year, so thank you very much. Okay, and ladies and gentlemen, or one lady and gentlemen, welcome to this session and to my talk. And this is my topic is exceptional points. We heard something about exceptional points yesterday by in Jörg Doppler's talk. Here we will be interested in what happens in scattering cross-sections in the vicinity and at second order and third order exceptional points. And this is work done in collaboration with Dieter Heiss from the University of Stellenbosch, as you may guess, because he's Mr. Exceptional Point, so everything that one does with him will be around the exceptional points. And I must also say thank you to the National Institute of Theoretical Physics of South Africa, Stellenbosch, and its director, Friedrich Scholz, who is also here, for having me there for the last 2 years and doing this sort of research that I'm telling you about today. Part of it was also in collaboration within my group, Holger Katayus, who is here, Lukas Schwarz, a bachelor student, and Jörg Mein, a senior scientist at the Institute. Okay, let's start. The outline is just a short introduction about exceptional points, then we turn to second order exceptional points, discuss the model, the scattering cross-sections, and discuss their profiles, and then we'll turn to third order exceptional points and repeat the same story for third order exceptional points and compare the results. Okay, exceptional points. As you heard already yesterday, they have unusual properties. The characteristic property is that two or more eigenvalues and eigenvectors coalesce in a branch point, that singularities. That is, to become not only the energy eigenvalues become degenerate, but also the eigenvectors align and become parallel identical. And the typical branch point singularity property is that at a second order exceptional point, you have a square root singularity. So if you have a parameter, physical parameter in physical space, which you can vary, and if you have this singularity, the square root singularity, if lambda becomes equal to the critical value at the exceptional point, here the EP2, the exceptional point of second order, you see we have this familiar behavior. The eigenvalues turn from real to complex. Similar in the case of EP3s, where you have a third order singularity. Of course, this characteristic property that eigenvectors become identical is not possible in Hermitian systems, but it's possible in non-Hermitian systems, in particular in open quantum systems, where you have loss and gain, for example.
It's not plus or minus.
Oh yes, of course, yeah, that's right. It's just the plus. Okay, so the Riemann sheath that you also saw yesterday for the EP2, the characteristic property is that you have these two Riemann sheaths corresponding to the square root of the complex square root, and if you encircle the exceptional point, you get from one Riemann sheath to the other, and then you go up again. And so you have to circle the eigenvalues twice in order that they become identical. That is, the eigenvalues and eigenvectors interchange when encircling the EP2. It's more complicated or a richer structure for EP3s, as first discussed by Eva Maria in her publication on coalescence of three eigenfunctions. Here you have three Riemann sheaths. But what can happen is that you encircle the exceptional point. You go from one to the next Riemann sheath and then to the third. So you have to go 3 times around the exceptional point before you end up at the original position again in this physical parameters space. But there is also a version where one of the circles is just detached from the other Riemann sheet. So if you go from one, you go down to the other one, and then you return to the first one again. So this is similar to an EP2 behavior, but is in fact an EP3. So, and in addition, the eigenvectors accumulate an additional geometrical phase when encircling the EP. You get plus and minus signs. So, and what, in contrast to the usual behavior of the scattering amplitude at one resonance, the coalescence of two or more resonances in the continuum invokes poles of higher order in the Green's function, in addition to the usual first order pole. This is for the case of the EP2, you have the ordinary pole, but you also have a second order pole. And even more complicated for an EP3, we have the first order, the second order, and a third order pole. And the purpose of this talk is to explore this merging of first order poles with additional higher order poles at exceptional points, specifically here at second order and third order exceptional points, and what happens to the cross. You could have higher order poles if you have an EP4, but let's progress slowly, 2 to 3 inductively. Okay, so let's turn to the second order exceptional points. The model. The model is a classical system of two driven coupled oscillators with damping, and this is used to mimic the general behavior of a two-channel T matrix in open quantum systems when an EP2 is approached. So you may wonder, well, this guy is talking about cross-sections, quantum mechanical cross-sections, then he starts with a classical system. What's the reason for that? We only need a system which exhibits an EP2, an exceptional point of second order. And in particular, as I will demonstrate, in the vicinity of the exceptional point, any problem that you have with an exceptional point can be mapped on the behavior that we find for this system. So what we have is two masses coupled to the walls with spring constants F1 and F2, and damping constants gamma 1 and gamma 2, and coupled by a spring with spring constant F0, gamma 0, the damping of it. I should add that this model with classical oscillators has been used in literature quite often, of course. I just mentioned this paper by Joey et al. From Korea on classical analogy of Fano resonances. And Fano resonances are resonances with asymmetric profiles. Another paper is the classical Fano oscillator, same model. And Satpariyaram, Fano interference in classical oscillators. So you see, you have this quantum mechanical effect of Fano resonances, but in classical oscillators. And in particular, in metamaterials that were mentioned yesterday, if you couple the split ring resonators, you use the same model of classical oscillators coupling the split ring oscillators. So this is the mechanism of Fano resonances in coupled plasmonic systems. So you see this has also entered the field of metamaterials by now. Okay, in the following we choose equal masses. The coupling spring constant will be called F, and the unperturbed frequencies omega 1, omega 2, which correspond to the unperturbed oscillations of M1 and M2. Damping constants in the following will be called K1 and K2 instead of gamma 1. And what is important, the damping constant of the coupling spring will be G. So F, the spring constant, and G, the damping constant. And the displacements are denoted by Q1, of course. And then we have an external force acting on the system with a periodic frequency, with a frequency omega, which can be turned on and off. And we will look for resonances, we will look for values of driving frequencies where you finally get an EP. So the equations of motion, classical equations of motion for this system can be written in this form in phase space, that the phase space vector, that's time derivative, is m times, this is this matrix, times the phase space vector plus the driving force, external force. And the matrix M, you see they have all the damping constants, the frequencies, the damping constants of these individual springs, K1, K2, of the coupling spring, and this is just the definition of the momenta. So if we assume time periodic solutions with the frequency of the external force. You take the time derivative, and then you end up with an equation where you get a minus I omega on this side, and if you bring it on the same side, you see that the solution is that you take the inverse of minus I omega minus m on the driving force, and then you in principle have the solution. And resonances would of course occur when this denominator, when this matrix becomes singular. That is, when the secular equation becomes zero. This would produce real resonances. But if you want to have two resonances coalesce, we also have to require that the first derivative of the characteristic polynomial vanishes. So this is for complex values of omega. Okay, so thus to find the exceptional points, you have to set up the characteristic polynomial of this matrix M, which I chose to decompose in a matrix M naught, like this, and F times a matrix M. F was the coupling spring, the spring constant of the coupling spring. So solving the two EP2 equations, characteristic polynomial equals 0 and its derivative with respect to omega, leads to 4 real valued equations for 8 real parameters. The frequencies of the individual springs, their couplings, the damping of the coupling spring constant, and of course the real and imaginary part of the frequency that I was looking for. Now, the characteristic polynomial is a polynomial of fourth order, so you find all the solutions, but the art is to find solutions where the physical constraints are fulfilled, namely that the spring and coupling constants of the coupling spring, of course, should be greater 0, the damping greater 0. The real part of omega should be greater than 1, and an imaginary part less than 1, because we want to have a resonance with a width.
And the gammas, where did the gammas go?
The gamma has become the case. Yeah, it's just our notation and Dieter Heiss's notation.
Why does omega have any imaginary part?
Because it's pardon?
Is omega not the driving?
Yeah, but if you have an imaginary part, you'll have a resonance. You have a width.
Yeah, but isn't omega something? Is it not something that you impose? Is it not an external parameter? Omega.
Omega is an external parameter. Yeah.
So why?
You have a polynomial of fourth order, and which has 4 solutions for what you call for roots, and they may be complex just from.
But is it not something that you impose?
No, but they evolve for a particular value at which it will produce a resonance.
Okay.
But you're asking how would you actually, from the outside, drive with a complex
Yeah, he's
frequency?
asking physical reason.
Because
Okay.
you can drive with a real frequency.
You can drive
Does
with
that
a real
mean you're
frequency.
just driving it harder and harder and harder? Is that
Well,
weaker and weaker? I mean, is that?
Yeah, in principle, you can drive with a complex frequency if you want.
Yeah, I mean, it just means that you're
it's
pushing
that
it
it's
harder.
pushing it out, yeah. Harder, or less and less, yeah.
I mean, physically.
Yeah, of course, it will be the real part becomes growing exponential or decaying exponential.
So we have 8 real parameters, but only 4 equations. So we assume the individual oscillators to be undamped. Then we remain with 6 parameters. Then we have, and then if we prescribe omega 1 and omega 2, then we can get the solutions for G, F, and the frequency. And this field, then you can in fact give the real and imaginary part where both equations are fulfilled. The characteristic polynomial is 0, and its derivative also express in terms of the frequencies of the individual oscillator. The real part, the imaginary part at the exceptional point, and also the damping constant that is necessary to produce that exceptional point, and also the spring constant. Okay, so now in the close vicinity of an exceptional point of a higher dimensional eigenvalue problem with a complex matrix decomposed like this can be reduced to an effective two-matrix, two-channel scattering problem. And this is true for any problem where you encounter an EP2. Now we decompose it in this form. We have a 2x2 matrix finally, where the capital omega 1, omega 2 are still related in our model to the original physical quantities, well, of no particular interest here. I don't give the explicit forms. And then you have a 2x2 matrix with quantities epsilon 1, epsilon 2, epsilon 1, which also are still related to the original physical parameters, but not given here, but it will assume this form for any system where you encounter an exceptional point of second order. And the advantage of doing this is that the Green's function, and thus the scattering amplitudes, both near the exceptional points, can be written in an analytic form. Here, this is near the exceptional point. You see, now I have switched from omega to E, just to insinuate that any problem where you have an energy, where you have poles in terms of energy, will be represented can be represented in this form. So we have here the first pole E1 corresponds to our, in principle, to our omega 1 in the first part, and here's the second pole. And this is the Green's function in the vicinity and at the exceptional point, which is expressed in terms of these reduced quantities I just mentioned before. It has a pole of first order, of course only at the value of at the exceptional point, and a pole of second order, as I mentioned before, and this can be written in explicit form for the case of an EP2. So as I already mentioned, we know coalescence of two resonances leads to a pole of second order in addition to the usual first order pole. Now we, I should mention that of course in the reduction to the 2 dimensional problem, the value of the EP and its vicinity remains the same. The energy trajectories, eigenvalue trajectories in the vicinity are of course the same. So to calculate now scattering amplitudes, we introduce the T matrix, transfer matrix, like this in the ordinary form, and cross sections 1, 1 and 2, 2 are given for 2, 2, 2, 2, for example, by the second term VGV, and this is the explicit form of the T matrix, expressed again in these reduced quantities, which in any EP2 problem would be different, but in our model we can give them explicitly. Okay, so cross sections at and away from an EP. So here let's go see. The driving frequency in our model now is for the one oscillator in some arbitrary units 2, and the other one is 2.1. And here we are at the spring constant has the value of the exceptional point. Energy or frequency. See, you have an asymmetric line profile, and if you go away, and this is the position of the exceptional point, if you go away from the exceptional point, that is, we increase the spring constant by 0.3, still an asymmetric line profile, and a 0 in particular at the exceptional point, and the same if you are even further away from the exceptional point. I should say that these are our canonical parameters for the frequencies that are used in the following, but here is also our examples. What happens if we take these canonical frequencies and introduce damping in 1 for 1 of the two oscillators? Then you see it's still an asymmetric line profile. Here would be the exceptional point, but it's no longer a 0. And the same if you increase the damping, it looks like this. And also if we go back to the undamped case and we use a much stronger frequency, a higher frequency for the second oscillator, still asymmetric line profiles, an exceptional point, but no longer a 0. It's interesting to look at the individual contributions that produce in the upper row, where we have no damping for the individual oscillators, these line profiles. Now, let's approach the the exceptional point just far away, 0.5. This is this picture here. And the individual contribution, here's again, this is the cross section. And these are the individual contributions of the pole terms away from the exceptional point. So we have two peaks here, and each peak here can be associated with one resonance pole. The big one is this one, the blue one produces this one, and the black one is the interference term. Of course, the first order poles also produce an interference because we have two terms. So you see that this interference term is small compared to the other ones, but to the height of the peaks, but it forces the vanishing of the cross-section at the exceptional point. Small, but forces the vanishing of the scattering, as it says here. Now we get closer to the cross-section. This was the cross-section I showed before, the individual contributions of the pole terms, the blue one and the red one. And now you see if they alone could not be resolved separately, because they would be overlapping resonances. And the interference term is now much bigger and determines not only the position of the zero of the cross-section, but also the position of these peaks, because it's no longer the peak is no longer at this position, but it's influenced by the interference terms. Okay, that's all ready. Now at the exceptional point, what happens there? This is the cross-section at the exceptional point, and the individual contributions. So of course, at the exceptional point, they are the cross-sections are identical, the blue one and the red one, and this is the interference term. So here the interference term is now given by the interference of the first order pole and the second order pole terms. And clearly the zero in the cross-section, that is no scattering, it's transparent, is caused by the interference term, clearly. So you have the all-important property that the interference term causes an asymmetric line profile and a vanishing at the cross-section at the exceptional point. Okay, asymmetric line profiles can be encountered in physics in many areas, and are called Fano profiles. It's an interaction of a quasi-bound state in the continuum with a continuum channel, and this always gives rise to an interference and asymmetric line profiles, for example, in photoionization cross-sections, in the transmission through waveguides, or nano waveguides, and so on, and also in metamaterials. Okay, so we tried to fit the asymmetric line profiles with the Fano formula. The Fano formula is given here, the cross-section. You have the reduced energy. The reduced energy is the distance from the resonance divided by its width. And Q is the Fano parameter, the asymmetry parameter that determines the asymmetry of the profiles. And here is a fit with a single, with this Fano formula at the exceptional point. And you see locally the vanishing, you see the zero line is here, the line profile can be modeled at the exceptional point in terms of the Fano formula. Further away, it's still possible, but of course it fails if you're further away. So it only works locally. So the idea was why not introduce two Fano parameters, and so we take the left part of the cross-section and model it by the Fano formula, and the right part. So of course you have different Fano parameters to the left and the right side, but it works. And also further away, but of course not globally, but only locally. But then we came across a paper by Magunov et al. Published in 2003, where they introduced the idea of energy-dependent Fano parameters, asymmetry parameters. And their formula for the cross-section looks like this. So you have a similarity with the original Fano formula, but now with an energy-dependent Fano parameter. And the function eta is defined like this. Here enters the position of the second resonance, and this is the energy-dependent Fano parameter. And here I'll show from top to bottom what happens, again, for our model parameters, omega 1 equals 2 and omega 2 equals 2.1. Away from the exceptional point, 0.3 plus, you see, almost identical fit. Blue the cross-section, red fit with the energy-dependent Q. Closer to the, further away from the exceptional point, and also very far away from the exceptional point. You see, it's still a nice fit except for this outlier here at the first peak. So there is an excellent agreement, in fact, with what can be obtained with this formula. But you may ask, what happens at the exceptional point? There you can fit the cross-section also with this formula, but it turns out that the second resonance would have to have a negative width, which of course is unphysical, which means that this formula or the theory that in the regime of overlapping resonances, the cross-section can be described by a Fano resonance is a energy-dependent Fano parameter that fails. But this is to be expected. Okay, this was just an excursion that, in fact, these asymmetric line profiles can be modeled by the Fano formula and interpreted in terms of Fano profiles. Okay, the conclusions for the EP2, while approaching the EP2, the asymmetry of the line profiles is caused to an increasing extent by the interference term, while the pole terms become more and more equal until they coalesce at the exceptional point. And then neither of the two peaks can be identified with a single resonance pole, and the interference always produces a zero, a no scattering at an energy between the two peaks for different parameters. As I just demonstrated to you, if you have damping of one of constants, a minimum. And the line shapes can be modeled by Fano profile. Now, does this carry over to third order exceptional point? Well, again, the model. I should mention that there has been interest in third order exceptional point over the years, and I think one of the most important papers was this one here by Eva Maria, signatures of 3 coalescing eigenfunctions, which are our interest in EP3s, in fact. But there are other papers by Ryu et al., analysis of multiple exceptional points related to 3 interacting eigenmodes in Hermitian Hamiltonians. We also found third order exceptional points in our theoretical work on bifurcations in dipolar Bose-Einstein condensates in multi-well potentials, and there's a paper by my Moiseyev group where they analyze the Bloch equations, and they also encounter 3 exceptional points of third order. And there are maybe more, and there certainly are more, which I didn't mention. Okay, now so we just make a natural expansion of the model that we had before. 3 driven coupled oscillators with 3 different masses, with unperturbed eigenfrequencies omega 1, omega 2, or 3, and damping constants k1 to k3, as before. And 3 coupling springs. Now we have you could imagine a star-like arrangement or in a triangle, that the coupling springs between mass 1 and mass 2, with spring constant mass 1 and mass 3 and mass 2 and mass 3, and associated damping. So you have 3 coupling springs connecting the 3 masses individually. And again, we have an external driving frequency. Displacements, now 3 displacements, momenta P1, P2, P3. So the equations of motion, as you can imagine, now take a more complicated form. It's a 6-dimensional space. It looks like this. Here we have the initial conditions for the driving force and the driving frequency. And this is what the matrix M looks like. Rather involved, of course. And these terms, note that these terms occur because the time derivative and the momenta, of course, you have to divide by the masses in order to get the T1 point.
P parameters, you should only have C parameters because forces are derivative of time of the momentum, right?
Pardon?
The driving forces, you have 3 Ds. And the
Okay.
the Ds drive the Qs.
No, they can be.
forces
Well, they're written here, but they take for 0. Right. And
I'm sorry. Why do you need any driving? I mean, we are discussing an eigenvalue
Okay.
for these exceptional points.
yeah, we have to look for the exceptional point. For the driving frequency arises the exceptional point arises in the complex plane of
Yeah.
omega.
So you just
So
study eigenvalues and eigenvectors of this complex non-Hermitian Hamiltonian. Why to drive it? It's a problem. Isn't this a problem of eigenvalues to locate this exceptional
But
point?
it's
No,
performing an experiment. So
Uh,
it's your
Okay, no, the point. The,
Let's forget it.
no, the point is
Don't introduce engineering.
we assume, of course, now that all the p's, all the q's are proportional to e to the minus I1 omega t.
Yes, but
Then
I'm asking, what if I just study the eigenvalue problem?
you mean
No
just,
external driving. I switch off the driving. I'm asking,
but that's not that's.
what is the eigenvalues of the...
Yeah, you can do that, but you will not find an exceptional point in that case.
Oh?
Because we have nothing to vary. We want to have
Well, we will find complex,
You-
we will find complex solutions of this eigenvalue. Complex eigenvalue.
Right. but we don't.
You can't find the experimental.
It's the spectral parameter. Z is the
Spectral,
spectral.
omega is the spectral parameter.
Precisely Hamiltonian, which you can relate to this 6-dimensional classical phase space energy. Right? But it's not, I mean, this is not, the M is not a Hamiltonian.
Right, that's not a Hamiltonian. Right, yeah. And in particular, the resonances or the EPs, the position of them, will not depend on the initial conditions. Just like the position of resonances in a classical oscillator also depends on the physical parameters and not on the initial conditions. Now this is, of course, complicated. And EP3s now occur for complex value of omega, where the characteristic polynomial vanishes, its first derivative, and its second derivative with respect to omega. So we have, because now you want to have 3 identical values of omega at the point that is. Also the second derivative has to vanish. And this leads to 6 real-valued equations for 17 real parameters. The frequencies of the individual oscillators, the damping, the masses, the coupling, the dampings, and the coupling, and the spring constants of the coupling constants, and of course, what we are looking for, the real and part and the imaginary part of omega. Now this is, of course, too heavy. And the special case that we looked at was that oscillators themselves are undamped. So the case 0 again. And we have no coupling between oscillator 1 and 3, which would be this triangular arrangement, so where where there's coupling between 1 and 2 and 2 and 3, but not between 1 and 3. So this leaves us with, let's see, 1 to 5, 12 physical parameters. So still a lot. And but it leads to a simpler matrix M, like this. So the F2, F1, 3, and so on have disappeared. Now these equations can only be self-numerical, of course. And if we now prescribe values for the 3 masses, 3, and the oscillator frequencies, 6, then we have 6 still 6 unknowns, but 6 equations, 6 real-valued equations, which can be solved. So it's the 4 parameters are the spring constant, the coupling, spring constants, and the damping, and then plus the real part and the omega. And of course, complex solutions can always be found. Again, the art is to find solutions which fulfill the physical constraints of the coupling, the frequency, the spring constants of the coupling from 1 to 2 and 2 to 3 should be positive, of course, and also their damping should be real and positive, we find a complex omega with a small negative imaginary part, because if it's too far away from the real axis, it will have no effect on the cross section. To satisfy the constraint, it needs some search, and I could explain it, but I just turn to an example, which is for 3 different masses. I should mention that if we take 2 masses equal, we didn't find an EP3. So for this set of values of the masses 1 through 4 and this set of frequencies, an acceptable solution is found at this value of omega, 0.89 minus I is 0.071. And these are the corresponding coupling constants. So we have to search in this physical parameter space with the which are given by the F's and the G's values, so that the 3 eigenvalues coalesce. Okay, so and again we reduce the 6-dimensional problem to a lower dimensional problem. In this case, it gets down to a 3-dimensional problem, because we have 3 eigenvectors, and so we use the almost 3-fold degenerate eigenvectors in the vicinity to reduce the 6-dimensional matrix to an effective 3-dimensional problem with the same EP and also in its vicinity. This is analogous to what we did in the EP2 case. And you remember that I made a decomposition of the matrix, here I suggestively call it H, into a part M0, there, H0, plus F times an M1. And now the X, or we have a choice of what should be the X or the F for the 3-dimensional matrices around the value, and X now can be any of the 3 couplings. It was just F in the previous case, but now we can decompose it and just extract the term that belongs to F12 or F23, G12, G23. So the spring constants and the coupling constants. So there's a variety of choices to study the vicinity. And here's an example of eigenvalue trajectories for different couplings. So these are real part of omega, imaginary part. This is the position of the exceptional point that I just showed before. And these are the eigenvalue trajectories when the spring constant between mass 1 and 2 are moved away from the EP3. You see it sprouts out, as it has to be, in 3 branches, and at the end we have these 3 points. So we have one resonance with a large imaginary part, so it's a very broad resonance, and this would be a very small resonance. And now and on the right hand side, the eigenvalue trajectories are shown when the damping between 1 and 2 is moved away from the exceptional point, and all the other quantities at the exceptional point, F12, F23, are kept constant. Note that it's the same position at slightly below 0.9. That's the exceptional point, and here again, if we move away, we get one with a large width and with very narrow imaginary parts, a small imaginary part that is narrow widths. Okay, so consequence in the corresponding quantum mechanical problem. If we now assume we had derived this from a some quantum mechanical problem, scattering problem, we must expect very different scattering patterns in the immediate vicinity of the EP, depending on the choice of how we decompose our matrix. And even at the exceptional point, we expect differences in the T matrix, since the T matrix depended on how you decompose of the original matrix or Hamiltonian. Okay, away from the EP3, the Green's function has 3 first-order poles as the spectrum of H, but as the EP, as we now already know, it has poles of higher order, just like this, and here I is the identity matrix. In contrast to the 2-dimensional problem, there is no explicit form for the Green's function here anymore, so we have to calculate everything numerically. And here are now scattering cross-sections at and near the EP3. If we decompose the part depending on the spring constant between mass and 1, coupling constant between the coupling spring of between mass and 1 at the EP as a function, now it's T11, but it's for T22 it's quite similar. You see, again we have a funny profile on this asymmetric line profile, and if we now decompose this cross section in the individual poles, now we have, of course, maybe I could just go back again. If we now take the square of H1 G H1, of course, you have the pole terms. So we have the square, the modulus squared of this term, and of this term. This will be the sum of the poles. But then you have the interference between the first and second order pole, between the first and the third order pole, and between the second and third order pole. So we have 3 different interferences. Now this is the sum of the poles, and those are the interference terms. Here, see, one positive, one negative. So you have, and it's the interference terms that bring the sum of the poles to this funny line shape. Further away from the exceptional point, here we are 0.92. The cross section looks like this. Again, it has a 0, and then a broad distribution, a broad resonance. Sum of poles. So the modulus squared of the pole terms, like this. Evidently, this dominates, and you have those are the 2 resonances with narrow width, close to the imaginary or to the real axis. And if we sum the interference terms, they are no longer as big as here, as on the left, as at the exceptional point, but still the force is 0 at the cross section at the exceptional point. At some point. And if you remember the eigenvalue trajectories, I said that if you are far away from the exceptional point, then you have 1 resonance with a big width and 2 small ones, and this is exactly what you have at the exceptional point. That the individual terms look away from the exceptional point. Here we have to look at. This is the broad resonance, and this is the contribution of the 2 narrow resonances down here. Now these are the eigenvalue trajectories when we change the damping constant between 1 and 2. And again, if we now decompose in that way that we move away from the exceptional point by changing the damping constant, again we have a very funny line shape, and even away from the exceptional point, a very interesting line shape. And if just to demonstrate the variety of cross sections that you can obtain here, we also change the spring constant of between mass 1 and 2 and 3, and in this case we have no 0 at all. This just demonstrates that depending on the choice you may have very different cross sections. This is an example with less structure at the EP, where the interference has a less drastic effect, but it's still noticeable in that this, if you try to fit it with a Lorentzian, it doesn't work. So it's no longer an exact Lorentzian. Now, this was a classical problem, quantum mechanical interpretation, but we can also compare with the classical amplitudes. Here is shown the amplitude of the first oscillator, maximum amplitude, with all other oscillators initially at rest if we drive externally. And you see that the amplitude profile also assumes asymmetric line shapes further away from the from the EP. And again, in this case, it's the further away from the exceptional points is the contribution of these resonances that you can see. So the large one and the rather narrow one. But if at the I could have shown it here. These are the producing the narrow resonances here, and this is the big one on the other side. So that's quite understandable. But at the exceptional point, the classical amplitudes show little or no structure in contrast to the pronounced interference patterns in the scattering amplitudes, because you have not that sort of interference that we have in the Green's function. Okay, just a short summary. For an EP3 provides for a much richer structure than an exceptional point, but can such things be realized in the laboratory? One idea also proposed by Eva Maria was look at waveguides, and she has already produced a 3x3 matrix model where you get an EP3. And in fact, we are just trying to calculate the governing equations numerically, not just in the matrix model, but for the full propagation. Another idea would be have a microcavity with 3 partitions. You heard yesterday that exceptional points were found in microwave experiments where they had divided the microwave into 2 halves and had changed perturber and the width of the gap between the 2 regions. And this could of course be generalized to 3 partitions, and one could look for an EP3 there. Also, Bose-Einstein condensates in triple well potentials could be looked at, or should show exceptional points of this sort, and possibly in the analysis of the block equations of the Matveyev group that I mentioned at the beginning would also be a possible application. And there will be more. There may be more. And with this, I'm done, and I thank you for your attention.
Thank you for your interesting talk. Clear. Yeah, I'll take some questions according to order.
Well, as you're probably aware, in the 90s there was a whole industry in the so-called matrix model, or the theory of random matrices of large size, to look for multi-critical point of any kind, and that.
Mm-hmm.
And also in vector models. And also in vector models.
And also in
Vector
vector
models,
models,
yes.
and things like that. There's a whole industry.
Yes, of course. In that respect, it's what the matrix models are have experienced a revival.
All possible perturbations.
Yeah.
Like
So
that.
it's a revival matrix model.
So there were many coupling constants, and you were looking for positions in parameter space where the free energy would become critical, its third derivative, etc.
Exactly. That's quite analogous, right? Yeah.
No. Okay.
I assume that in your system, the time reversal symmetry is explicitly broken, right? Because you have spatial. So
Because I have what?
Friction.
Friction. Oh
you
yes,
have a
of course.
friction, so that time reversal symmetry is
Right.
explicitly broken. But in general open quantum systems, it's of course not broken, and so the reason why I'm saying this is we found in quantum open systems, we found that there is also in this kind of open quantum system, there is also an exceptional point between resonance state and anti-resonance state, which is a time reversal state. And we found that Fano resonance also occur between the interference between resonance and
anti-resonance.
So in your case,
That's
it's
interesting.
always the collision of 2 resonances or
Right.
3 resonances.
Exactly.
But it's I think it's also nice. It would be also nice to see the interference between resonance and
Anti-resonance. That's interesting. So.
Yeah, if you have non-linearity in the system, it's known that in the usual resonance systems you have the non-linear detuning of the resonance. So strictly speaking, the resonance never occurs, but instead we may have some multi-stability close to it. So do you expect here, if we introduce some non-linearity, the very effect of the coalescence will survive, or it may be actually prevented?
I mean, we have looked at EP2s in double well potentials with nonlinearity, and there the coalescence still present. I don't know. You will not talk. Will you talk about it? No, okay. The exceptional point is there, but the coalescence scenario becomes more involved.
Yeah, but the effect itself survives, isn't it?
It survives, yeah. But the non-linearity influences the stability of the states
Yeah, like
sensitively.
the usual resonance.
Right. So in fact, it destroys it.
Adi?
One, you force the generalities, but how are you guaranteed that there will be exceptional points? But second, now I'm interested in what you said. Do you know that at any time you have a nonlinear equation with an exceptional point, it will be unstable? If you look into that in general.
In general, we've just looked at it in our Bose-Einstein condensates in double well potentials so far, and there the ground state becomes unstable, but there is one excited state that remains stable with nonlinearity.
Any other questions?
Yes, question actually. Do you think that this theory can be extended this time to the linear system, but when your drive is not direct but rather parametric?
Well, I think so, yeah.
Did you try to do it?
No, of course. Just hard enough to do that.
Eva?
So when you show, for example, if you in your classical oscillators, if you were to measure the amplitude for the function of time, so and if you did see three such peaks in this asymmetric, would you then say that you could conclude that there's an infinity, or could there still be just three resonances which, I mean, is this asymmetric profile already, if you saw something like that,
Yeah.
would you then say, okay, that means we only see three in the neighborhood, or conclusive would that be?
I don't think that's conclusive. I think
So
if you have an exceptional point and you go into the vicinity, then I would expect
Yeah.
something. But I think the other way around, it's not
could still
conclusive.
be just, it could be a VP2 in something else, right? And
Exactly.
could it be just three resonances, and would they make, I mean, they would still make a Farnow type.
Right. Well,
profile,
you have these are the three resonances that produce that profile. Yeah.
So, and you wouldn't be able to tell that somewhere they actually meet.
No.
Yes, both. After.
Still, I want to see clear this connection between the eigenvalue problem and the driven problem. So I have two coupled oscillators.
Mm-hmm.
I don't drive anything.
You don't play.
So I find two complex eigenfrequencies. Because there's loss, gain.
Yes, of course.
So I put 2 points in the complex omega plane.
Correct.
Now I'm changing some parameters, for instance, coupling. So these points move, I have trajectories. When they cross, this is the exceptional point. That's correct or not? This
If they cross, yeah.
okay, then,
We didn't check whether they cross.
well, that's, I think, many speakers here define this, just, plus, minus, square root. So there's no driving there.
Okay.
Now you're doing something else.
Uwe is really anxious to tell you something.
We need a spectrum.
You need more information. Because moving in the plane and they're going together, there might be a short structure of different type actually. When you have this very special structure, it might still remain kind of diagonalized. It might be a second or fourth block, and one eigenvalue at the same point, but which is out of this one block. But it might be also
That could exist. Yeah.
But here you drive, so you're already
So
asked.
I drive because we need a
Omega is
what-
drive with the real frequency.
what we are looking for is a spectrum, eigenvalue,
But
and that's the omega.
for the eigenvalue problem, you don't drive.
But Boris,
But that's
in
a
engineering
conventional
experiments, in the students' lab, when they study this resonance, they drive with real frequency.
They need
And they
to have
see
a
the
driving
resonance.
license.
No, but look, I mean, when you say that two coupled oscillators and eigenvalue problem, that's a quantum oscillator with eigenvalue problem.
Well, but
right?
he
One
no,
of
the
classical
spectrum
quantum.
is just the spectrum
Exactly.
of M.
Yeah,
This,
no,
this
it's
is the
not,
spectrum
right?
of
I mean,
M.
that's the whole point.
Right.
In the
So that's what
classical-
he's saying.
In the classical
And I think
system, the
that's true.
definition
I
of what a
think you're right.
resonance is, or what an eigenvalue is the response of a system to an external driver, right?
Yeah. That's what a resonance is.
No, no,
That's
he's just saying that this is the spectrum of M, right?
No, it's not.
Yes, it is. I mean, he calculates determinant M minus I omega.
And looks for the zeros.
So
of
The zeros, yeah.
That's
Yeah.
that's the spectrum.
Yeah, that's a spectrum.
Yeah. So that's what he's saying.
So, Miroslav?
There is a fitting problem with tunnel on EP3.
Well,
Something like
no,
that.
we have not tried that. We've thought about it. Just like I haven't looked up in the literature. If you have a state, a quasi-bound state in the continuum coupling to two channels, there's certain, but there's multi-channel theory.
Those bound states in continuum is another physics put in. So this those two things together is interesting.
I would suppose so, but I thought about it, not to find the time to look at it.
Any other questions? Okay. If not, let's take